Okay, I think we are just about ready to start. So, Professor Zoubin Ghahramani, dear colleagues, dear students, dear guests, welcome to this Hans Christian Ørsted Lecture. My name is Rasmus Larsen. I'm the provost of the university, and it's a particular nice thing for me today to bid welcome to this lecture because it lies so close to the field that once was my own research field. And it seems that there's been a bit doubt of where the lecture was to go on, but I can assure you it is in this auditorium. We all know it's quite evident today that the data sciences are making their way into every scientific field. In fact, almost every human endeavor, from the natural sciences over the social sciences to the humanities. And we are so lucky today that the lecturer of the day, Professor Ghahramani, is one of the world leaders in exactly this field, helping to push this development forward. Professor Ghahramani's work is characterized by being at the same time fundamental science and of high relevance to real-world applications. And this has become eminently clear when it was announced just last month that Professor Ghahramani will take up a new position as chief scientist with the Uber company in just a little while. Now, the Hans Christian Ørsted Lecture series. As you all are undoubtedly aware, Hans Christian Ørsted is the founder of this university, and the series here was introduced in 1998. Twice a year, we invite outstanding scientists to give a lecture about their research and their more general views on the development in science and technology. We find that these lectures are excellent for bringing together researchers and students from all across DTU, as well as other interested parties outside the university. The current status of science and technology, the front seat of science and technology, is really something that concerns us all. I will now hand over the microphone to Professor Carsten Vedel Jacobsen, who will give an introduction to the speaker. But before I do that, I will just take this opportunity to thank the Hans Christian Ørsted Lecture Committee, Professor Søren Molin, Professor Viggo Tvergaard, and Professor Carsten Vedel Jacobsen for their work in planning this lecture series. As always, you have done a highly competent job, and I'm very much looking forward to hearing today's lecture. Thank you.
Thank you. So, ladies and gentlemen, Professor Ghahramani, it's a great pleasure and honor to introduce Professor Zoubin Ghahramani as today's Ørsted lecturer. Zoubin Ghahramani spent his early childhood in Iran and the former Soviet Union, and he then moved to Spain and later to the US, where he received a dual major in cognitive science and in computer science and engineering. This is from the University of Pennsylvania in 1990. He did his PhD in cognitive neuroscience at MIT, and he then moved to Toronto as a postdoctoral fellow in the Artificial Intelligence Lab of the Department of Computer Science. From 1998 to 2005, he was at the Gatsby Computational Neuroscience Unit at the University of College London, and he is now Professor of Information Engineering at the University of Cambridge. He's also a Cambridge Liaison Director and founding executive board member of the Alan Turing Institute. You can also see some of the affiliations up there, I can see. And he's also a fellow of St. John's College in Cambridge. And as Rasmus just mentioned, he is also now a co-director at Uber's Artificial Intelligence Laboratory. Professor Ghahramani is a world leader within the rapidly expanding field of machine learning. He is particularly known for his Bayesian approaches to machine learning, artificial intelligence, statistics, and data science in general. One of his more recent research interests, which I'm sure we shall hear more about today, is the development of a so-called automatic statistician, where the ultimate aim is to produce an artificially intelligent system for statistics and the data sciences to help people make sense of their data. Professor Ghahramani has a very substantial scientific production of more than 250 scientific papers, and according to Google, his scientific work has been cited more than 36,000 times, and the so-called H-index, if you're interested in that, is around 80. And Professor Ghahramani was also elected Fellow of the Royal Society in 2015. Okay. So with this introduction, please, Professor Ghahramani, would you take the stage and give your lecture?
Great, thank you for that introduction, and it's a pleasure to have lots of people here in the audience. I hope you find this interesting. So I'm going to talk about machine learning, artificial intelligence, and the automation of the data sciences. And I want to spend just a little bit motivating, as you've heard already from the provost, the importance of data science in our modern society. So we're living in an information revolution, and I have a picture of the Industrial Revolution here because I think that actually it's comparable to the changes that happened in society for the Industrial Revolution. And data is really changing society in many ways. It's changing the way we do the sciences. Sciences have become much more data intensive, and it's changing the business world as well. And all of this data on its own is not very useful. It just fills hard drives unless you have tools for understanding the data, for making predictions and decisions on the basis of this data. So that's really the goal of data science and the related area of machine learning. Let me spend one slide talking about the Alan Turing Institute, which is a very exciting venture that's been running for about a year in the UK. This is the UK's National Research Institute for Data Science, and it's located right by King's Cross St. Pancras train station in the British Library, within the physical location of the British Library. It's a joint venture between 5 universities: Cambridge, Edinburgh, Oxford, UCL, and Warwick. And it brings together people from many different fields, including kind of the broad definition of data science: statisticians, computer scientists, social scientists, people from the natural sciences, and mathematicians. And the goal is really to advance the field of data science. Kind of an exciting venture that I've been involved in for the past year quite heavily. So let me just dive into this sort of topic of machine learning. Data science is a very broad area. Machine learning, you could think, is a somewhat narrower area. It's the area that I most associate myself with. So what is machine learning? Well, there are many related terms to machine learning. The fashions come and go, so people used to talk a lot about data mining and neural networks, and those are maybe less in fashion now, but that has been replaced by other topics like deep learning. There's sort of terms like data science that appear and disappear. Potentially in the future, they'll disappear. Pattern recognition is a sort of old term that's been around for a long time. All of these terms are related, and machine learning lives somewhere in the middle of a lot of these terms. There are also many related academic fields. So if you look for machine learning research groups around the world, you will find them sometimes in computer science departments, sometimes closely related to statistics, obviously, because statistics is the mathematics of learning from data. I happen to be in an engineering department. As you've heard, people in machine learning sometimes have backgrounds or interests in areas like computational neuroscience and cognitive science, even fields like economics, which deal with rational decision making, have something to inform machine learning. And of course, applied mathematics, physics, et cetera, et cetera. But what's really made machine learning incredibly exciting in the last few years is the many, many applications of machine learning that you see around you in the world. So machine learning itself, I think of as the invisible thing that drives the algorithms that make all these other things possible. So of course, these things have been around, areas like bioinformatics, robotics, computer vision, natural language processing, etc. But the use of machine learning tools has created substantial advances in many of these fields. I've just listed a few of these application areas, and I'll go a little bit more in detail just to give you a feeling of where machine learning is impacting us in our daily lives right now. So one clear example is in speech and language technologies, automatic speech recognition, machine translation, question answering systems, dialogue systems, etc. These are all driven in part by machine learning technologies. Computer vision, an area that's been around obviously for a very long time, getting computers to recognize objects, faces, handwriting, etc. from images. Although computer vision research has been around for a very long time, only recently are we getting, I would say, somewhat spectacular results like what we have here, where an algorithm is presented with an image it hasn't seen before, and it's able to produce a caption. For example, in this case, man in black shirt is playing guitar, just by looking at the pixels in this image. And of course, you could critique these results. These are hand-chosen from one of the state-of-the-art papers in the field. And there are many failure cases still, but the fact that we're able to come anywhere close to going from image pixels to text description of what's happening in those pixels is really remarkable, and it took the whole field by surprise. There are other examples that we're now extremely used to, which we take for granted, which is probably most of you have a phone or camera that puts a little box around people's faces. That's a bit of machine learning that's running on your phone that's doing face detection. We just take these things for granted now. The fields of scientific data analysis have been transformed and are continuing to be transformed by the use of machine learning. I have a couple of examples here. This is gene microarray data, a format of data that is quite hard to analyze just by humans looking at patterns of overexpression and underexpression of genes. But if you use machine learning methods, you can extract patterns much more efficiently from these things. Here's an image of a robot scientist. That's not the robot scientist. The robot scientist is behind him. This is a system that was developed a few years ago which used machine learning to generate hypotheses, design experiments in a biological domain, execute those experiments, collect the data, and update the hypotheses. So full closed loop scientific data analysis done by a computer. We are constantly bombarded by people trying to sell us things, and whenever we buy something online, then we get recommended other things to buy. And that whole field of recommender systems is driven by machine learning algorithms. Self-driving cars is an area that is very heavily driven by machine learning algorithms. It's not a new area. It's very topical now, but there is for example, I've produced this slide here from a system called Alvin from the 1980s. This slide says, Alvin drives 70 miles per hour on highways. This is a self-driving car system from the 1980s. It would have been very, very frightening to be anywhere close to Alvin back then at 70 miles per hour. It was using a neural network, surprisingly, same kind of thing that people are trying to use now, except you could see it was a pretty small neural network that was taking the image and trying to steer the car. The world has moved on quite a bit. This is an image from the DARPA Grand Challenge, self-driving cars, and this is an image of Uber's self-driving cars, which are now deployed in Pittsburgh, San Francisco, and a couple of other places. I've ridden in one of these self-driving cars in San Francisco, in the rain, with traffic, pedestrians, cyclists, etc. around. It still has a human safety driver to make sure that the car, that the human can take control over the car in case it's about to get into a dangerous situation. But the fact that we're nearly there is going to have a tremendous impact, as you can imagine. Robotics, I love to show these robotic dogs playing football. You should watch the videos. They're actually absolutely hilarious. But robotics is another field that has been transformed and is continuing to be transformed by machine learning. Financial prediction, automated trading, computer games. This is from Google DeepMind's world-class Atari game-playing system from a couple of years ago, where their system basically learned to play Atari games at better than human abilities on around half of the games. Okay, superhuman abilities on computer games. Then they moved on to Go, and they're now competing against the world champions. So they competed against one of the world champions, and now they're competing against another one of the world champions at Go. And I will bet on AlphaGo winning that match as well. Does anybody know what this is? It's a little bit cryptic. This is a recent breakthrough in computers playing poker. So the computer system, this is Libratus from Carnegie Mellon University. It was playing against a bunch of world-class poker players. All of the numbers in parentheses are negative numbers, okay? So it managed to beat all of these world-class poker players. And poker is a particularly interesting game because it's a game where there is a lot of hidden state. There is bluffing. It's maybe potentially a psychological game, you could imagine, and so on. But not really a frontier that machine learning can't enter yet. In fact, this team at CMU, another team at Alberta, are among the world leading poker players now. Okay, so machine learning is this incredibly exciting area right now. It's very interdisciplinary, and there's a lot going on. So that's what I've tried to motivate in the first few minutes. But what is it? So, I'll start out, in the interest of the whole audience, I'll start out with some basic or canonical problems in machine learning to describe what is basically happening under the hood for all of these machine learning methods. And then towards the second half of my talk, I will go on to the frontiers, the things that I find personally very exciting in the field of machine learning. So the canonical problems in machine learning are things like this: classification. So in classification, you have data that belongs to two or more classes, and your machine learning system is trying to learn to divide new data into one of the existing classes. So it's learning a boundary that it can use to predict new data. And there are many, many classification methods, so you could look in the literature and you'll find a gigantic collection of buzz phrases for different methods that are essentially different ways of doing classification. Okay, here are a few of them listed. Regression is the problem of predicting a continuous quantity, let's call it y, given some inputs, call them x. In this case, the data might look like these magenta dots, And regression is the problem of learning the function y of x and possibly learning about the uncertainty in that function. Again, these concepts are actually quite old. Linear regression is a few hundred years old, actually. But machine learning methods doing regression involve both these very classical methods and much more advanced methods that have nice properties when you have lots of data. Clustering is another canonical machine learning problem. In clustering, what you have is just a bunch of data. Imagine these blue dots. And you are trying to learn to group the data into groups so that similar data points fall into the same group. So in this case, the algorithm might have discovered 6 clusters in this data represented by these ellipses. Clustering is used in all sorts of fields to understand and organize your data, and there are many algorithms that go back decades for clustering. Dimensionality reduction. Often your data is very high dimensional, and you want to either understand the low-dimensional manifold that your data lives on, or you want to be able to compress your data down to a small number of dimensions so that you can more easily process it and do some further learning on it. So the field of dimensionality reduction, as I said, maps high-dimensional data onto low dimensions while preserving relevant information. And again, there are many methods going back to PCA and factor analysis are over 100 years old, and some of these are much more recent. Semi-supervised learning, here we have a combination of labeled and unlabeled data, and we might have a small amount of labeled data, for example, these crosses and minuses, and a lot of unlabeled data, like all of these little black dots. And what we're trying to do is combine the small amounts of potentially expensive to collect labeled data with the large amounts of unlabeled data so that we can get better prediction performance. And finally, the last canonical problem I'll mention is reinforcement learning. In reinforcement learning, the system is not passively receiving data, but the machine learning system, you think of it as an agent that receives data in the form of what you could call observed sensory inputs. And then the agent is able to take actions or make decisions that might change the state of the world that the agent lives in. So in this setting, the agent interacts with its world by taking actions, and the goal of the agent is to maximize its expected future rewards. So along with taking actions, the agent gets some rewards or punishments from its world, and its goal is to maximize its future rewards. Now, this sort of reinforcement learning paradigm is the one that drives a lot of these gaming breakthroughs. So, for example, in the case of both the Atari and the Go game playing systems, it was heavily based on reinforcement learning. Reinforcement learning is obviously also useful for things like self-driving cars, although you don't want to wait until you have an accident to give a punishment to the self-driving car to not do that again. Right? So it's quite a bit more difficult to do something like self-driving cars in the real world than it is to play a game in a simulator. So just to hammer in that we have a lot of progress to make still in machine learning and AI to get these things out. Okay, so that was basically a map of canonical problems in machine learning, and you can kind of organize, again, some of the different parts of the field. Like any scientific and academic field, there are different people with different backgrounds working on different methods. And so what I've done here is kind of very quickly sketched out some of the different methods that people work on in general. This list is not very complete. It's just kind of a sketch. But one important bubble that I want to talk about is this bubble here, which is the neural networks and deep learning bubble, because it's really been quite revolutionary. It's really had a massive impact on our ability to process perceptual data. a lot of the hype and excitement in the field has been focused on deep learning and neural networks. So let me talk about that for a couple of slides. And then we'll move on to see, well, what's beyond deep learning? Where do we go next from deep learning? So neural networks and deep learning. Now, these ideas have not, although they're very exciting now, they've been around for a long time. Actually, even in the 50s, people were thinking about AI systems that might be based on things like neurons connected to each other and learning from data. Okay. But a neural network, as sort of popularized in the previous wave of excitement in this field, which was in the 1980s, is essentially mostly just a function approximator. Okay, so let me describe that in this one slide. So imagine you're trying to learn a function that goes from some inputs x to some outputs y. And that might be, for example, from the inputs might be the pixels in an image, and the output might be the class label for what the object is in the image, let's say. That's the function that you're trying to learn. And like all machine learning problems, you have some data, pairs of x's and y's. And the neural network has some parameters. Theta, these are what are called the weights in the neural network. These are tunable parameters that we're going to tune to improve the function given data. And the neural network is just going to model this function as some sort of nonlinear function, generally of both the inputs, x, these are the inputs, and of the parameters, these weights, which I'm calling theta. Okay? And so this is the very simplest neural network you could think of. What it does is it takes a linear combination of the inputs through this sum, and then it passes them through a single nonlinearity. And this is something that you could use to do, so for example, binary classification into two classes. This model has actually been around for a long time. It's also called logistic regression, or various versions of this exist in the statistics literature. So that in itself is not a very interesting neural network. What makes neural networks more interesting is when you consider stacking these computations into multiple layers. And what that means is really that you're trying to represent this function from x to y as a composition of functions applied in succession. So each of those functions is one of the layers in this neural network. So this would be, for example, a one hidden layer or a two-layer neural network. So there are two layers of weights here. And this is another function, for example. And essentially, these are just functions that are trained using classical statistical criteria like maximizing likelihood or maximizing penalized likelihood, using traditional kind of optimization methods such as stochastic gradient descent optimization. So think of neural networks as function approximation with some classical statistics combined with some simple optimization methods. Okay? So that's been around. That was around since at least the 80s. But they kind of lost popularity until around 2012, when they suddenly exploded again onto the scene. And what happened then is, first of all, that the field got rebranded. It's now called deep learning. These deep learning systems are essentially neural network models similar to those popular in the 80s and 90s, but with a few important differences. One of them is that there were some architectural and algorithmic innovations. For example, people made the networks deeper, had more layers in the networks. They also learned that certain kinds of nonlinearities work better than others. So rectified linear units seem to work better than sigmoid units that people had before. There are some regularization methods like dropout that were introduced. There were some methods for dealing with time series, like LSTMs that were introduced at some point. So people discovered or rediscovered some of these tricks. But a few of the other important things that happened were that the data sets were vastly larger in 2012 than they were in the 1980s, because we had the web, basically, and we could collect millions of images and millions of documents, and the sciences had exploded in their capacity to collect data and so on. And so basically the world was awash with web-scale data. But that alone is not good enough, because you need large-scale compute facilities to deal with web-scale data, which we also didn't have in the 1980s. So we have compute facilities that live in data centers on the cloud, and we have the ability to use graphics processing units, GPUs, to learn these neural networks. And we also have much better software tools. We have software tools that make it really easy to implement a neural network. You can be a high school student and implement a neural network by going online and downloading one of these software tools. And you don't even really need to know calculus. You don't need to know what a derivative is, because the software does it for you. And you don't really need to know that you're maximizing likelihood. So you don't have to really know much statistics either. You don't even have to know that much programming to do this. And you certainly don't have to know about optimization. Optimization is something that you choose in a drop-down menu of what to do. Okay, so the barrier to entry is much lower, and there's been a huge amount of investment and media hype. So many, many more people have entered the field, and it's really exploded. But let's not forget that the basic tool is basically ways of representing functions trained using essentially classical statistical methods, using variations on classical optimization methods. So that's where deep learning is. And a lot of news articles have basically claimed that AI is solved. We have deep learning now. It's kind of a bit exciting because it's a little bit like the brain, and so the journalists can talk about the brain and how AI is like the brain now, et cetera, et cetera. But that's hype. That's quite overblown. First of all, the connection to the brain is very, very weak. Really, any self-respecting neuroscientist will look at these systems and say, that's got very little to do with how the brain works. Okay? Secondly, even as engineering tools, these deep learning methods have some limitations. So let's be honest about the limitations of current deep learning systems. They're very data hungry. So they've succeeded because people have thrown millions of data points at them in various cases. But if you try training a neural network with the amount of data that humans use to learn about particular concepts, you'll find that they are not really able to learn anywhere as quickly as a human or an animal might be able to learn. They're also very compute intensive to train and deploy. So they're not very practical from the point of view that, compute costs energy, and energy is money, and basically we really don't want to be wasting energy on doing this unless it's really, really important. They're very poor at representing uncertainty. So they'll often make predictions, and all neural networks actually give you some estimate of uncertainty, but that uncertainty is actually uncalibrated in the sense that you can't really trust the probabilities that come out of a neural network. And this is something that I've been particularly obsessed about, and I'll talk about more in the latter half of my talk. They're also easily fooled by adversarial examples. And that is, you can, if you haven't seen this, it's worth looking at these examples. That's examples that are imperceptibly different from other examples, but where the class label that's given, that the deep learning system gives, is completely wrong. So there might be a picture, for example, of a school bus that might be classified as a giraffe. And to us, it looks like a school bus. There's small variations in the pixels that were designed to make the network confidently say that that's a picture of a giraffe. Okay? So the fact that it's possible to create these adversarial examples means that these deep learning systems are confidently going to be giving the wrong answers in certain cases. So it's very difficult to trust them, which is kind of coming at the bottom of this slide here. So that's the easily fooled by adversarial examples. They're finicky to optimize. It's sometimes quite difficult to optimize these things, requiring a lot of expert knowledge and experimentation. And then they're uninterpretable black boxes. It's very difficult to know how your system works. They're lacking in transparency. They're therefore also difficult to trust. So imagine a real practical application of deep learning, an application that we might really care about. For example, if you're building a self-driving car, you'd really like to have a very good pedestrian detector, okay, to detect whether there is a pedestrian in front of the car or not, right? And we really want our systems to be extremely reliable. We don't want them to be easily fooled by any kind of weird examples. We want their confidences to be calibrated somehow. And if anything goes wrong, we want to be able to figure out what went wrong, right? So let's think about going beyond deep learning. And this is a very personal view. This is my thinking about what are, for me, the most exciting areas beyond deep learning. I'm not saying deep learning is not interesting. Every machine learning researcher should know about deep learning, but their knowledge shouldn't stop there. So the view of machine learning that my group and I take is one based on thinking of machine learning as probabilistic modeling. So the idea of a model is that it's a description of data that one could observe from a system. And that's an idea that I think is quite powerful in the sciences as well. If you think about scientific data analysis, we have models of scientific phenomena. We collect experimental data. And then the way we tell whether our model is a good model or not is we compare the predictions of our model to our experimental data. Machine learning should really be as scientific as that. When machines try to understand data, they should be trying to build models of the things that they're interested in, and they should be improving their models on the basis of whether they fit with the observed data or not. Now, models have inherent uncertainty in them because you make a lot of assumptions when you build a model. You have the structure of the model, you might have some parameters in your model, you might have some forms of noise associated with your model. All of those aspects of your model have some form of uncertainty associated with them. And the mathematical language for representing uncertainty is probability theory. So in the same way that calculus is the language for thinking about rates of change, probability theory is the mathematical language for representing uncertainty. And so we're going to use the mathematics of probability theory to represent all forms of uncertainty, and we're going to continue to use the mathematics of probability theory in what used to be called inverse probability and is now called Bayesian statistics, which is just applications of probability theory to infer unknown quantities from the observed data. So here is Bayesian statistics on one slide. And the basic idea is as follows. So it's a simple rule. This is Bayes' rule. And it tells you how to go from knowledge about models before observing data to knowledge about models after observing the data. So I'm going to have two kinds of things in my world. There is the data. That's the only, they're unobserved, sorry, there's observed quantities. The only observed quantity is the data, and everything else is unobserved. So everything that's not directly observed, I'm going to assume is uncertain to some extent, and I'm going to represent my uncertainty with a probability distribution over everything that is not directly observed. Okay, so I'm going to use data to represent all the measured quantities here in green, and hypotheses to represent anything that's unobserved or uncertain. That could be the model parameters, etc. And now Bayes' rule tells us how to do inference about hypotheses from data. So we start before observing the data with some representation of our uncertainty over plausible hypotheses. That's what's called the prior. And then every hypothesis, because it's sort of a well-formed model, it gives some probability to the observed data. That's called the likelihood. And Bayes' rule tells us multiply the prior by the likelihood, renormalize by summing over all of the hypotheses you're willing to consider, and that gives us the posterior distribution over hypotheses given data. And that's your state of belief about hypotheses now after you've observed the data. It's a simple rule for learning and prediction from data. Now, here is Bayes' rule applied to the sort of concepts in machine learning. So this is my obligatory one slide on Bayesian machine learning. And one of the points I want to make is that Bayes' rule itself is not a fundamental rule. It's actually a corollary of two simpler rules of probability theory called the sum rule and the product rule, which I've reproduced at the top of this slide. The sum rule and the product rule sound like boring things you would learn in a textbook, right? That you might forget about because they're boring, right? But if we substitute these x's and y's for the things that we care about, the things that we care about are models, maybe model parameters. So I'm going to use M for a model class, a sort of family of models, and theta for model parameters, sort of these tweakable parameters of a model, and D for data. Then I can write Bayes' rule for learning about the parameters of a model given data. And it's, again, the same as we had on the previous slide. It's the prior, which is our representation of the valid, sensible range that parameters might take before observing the data. And then by multiplying by the likelihood, we get the posterior, which is the range of parameters that are consistent with the data after observing the data. Okay? And you might say, well, this depends on the prior, and it does depend on the prior because different priors represent different modeling assumptions. So in modeling, you have only two things. You have the data and then assumptions. And the Bayesian method basically says the data is the data, that's fine. The assumptions, just represent them honestly, transparently, using probability distributions. And then once you have those two, everything else is automatic. It's not arbitrary. You get an answer, which is the posterior, at least if you can compute this thing exactly. So that's the learning rule. If I want to make predictions, then basically the sum rule and the product rule tell me that predictions need to take predictions from every possible parameter value and average them with respect to the posterior. So there's a natural ensembling over predictions. And we can do model comparison at the level of models as well here. Okay. So given all of these successes of deep learning that have really, if you look at these papers, they don't really talk about Bayesian inference or probabilities or so on. Why should we care about this probabilistic approach? So I would say we should care because calibrated models and prediction uncertainty are important. So we want to have systems that know when they don't know. And also this framework, this probabilistic framework, makes automatic many of the things that people are doing manually. Okay? So there is an automatic Bayesian Occam's razor, which is, for example, a way of automatically selecting the complexity of the model given the data. And these tools for complexity control and structure learning are going to be potentially very useful. So in the context of deep learning, actually, the marriage of Bayesian or probabilistic ideas with deep learning has been around for actually quite a long time. There are some seminal papers in the early 90s by David Mackay and Radford Neal, and also Jeff Hinton and Van Camp, and so on, all around the same time. And The advantage, so this is just some various different ways of implementing Bayesian deep learning, including some recent things that we've been doing. But the advantage of doing this is now when you're learning based on some data, this is like a neural network learning based on these dots, then if you're going to extrapolate outside of the range that you used to train your model, your neural network is going to have error bars that are much more sensible, that capture the fact that it's saying it doesn't know what's going on outside of the range of data that is observed. And we had a very nice workshop at the NIPS conference on this topic of Bayesian deep learning recently. So when do we really need probabilities? What are the things for which this probabilistic approach is essential? And these things relate to, unsurprisingly, this notion of uncertainty. So forecasting, anytime we're making forecasts in the world, we really want to be able to represent our uncertainty. When we want to make decisions, we need to know the consequences of our decision, of our actions now on the possible futures, and that represents some form of uncertainty. When we're learning from limited, noisy, and missing data, we need to capture uncertainty in the data. When we're learning complex, personalized models, like for medical applications or recommender systems, that needs to represent uncertainty. The whole field of data compression is based around probabilistic models. Every data compression, lossless data compression algorithm corresponds to a probability distribution over data. And this area of automating modeling, discovery, and experiment design is also heavily dependent on this probabilistic approach. So as I mentioned, I'm actually now involved with Uber as Uber's chief scientist. And so why would Uber care about any of these things? And if you look at a lot of the things that, as a company, Uber does, it involves understanding supply and demand for people moving between different places. So modeling and forecasting driver supply, modeling and forecasting rider prediction, making predictions about expected time of arrival of people from one place to another, questions about pricing and business intelligence, modeling traffic in cities, learning maps of the world, building self-driving cars, which is a very major program at Uber, all aspects of improving customer service, improving personalization, etc. So all of these things require the widest range of machine learning and AI methods to make more efficient. So in the last few minutes, what I'll do is I will just talk about the research areas that really drive me and excite me. And at one point, a couple of years ago, somebody asked me to give a talk about my research interests, and they said, you have to do it in one slide. So they forced me to produce this one slide, and it was actually quite a useful exercise because I realized that almost everything I'm interested in is centered on this single theme, which is automating machine learning. So a lot of machine learning now, ironically, is very labor intensive in the sense that experts sit there with the algorithms that they know, and they hand tweak the algorithms, and they run them on some computer, and then they tweak them again, and then they give up after they get tired, right? And that's really the state of affairs right now. And for anybody with a kind of passion for optimizing things, this is a very suboptimal state of affairs to be in. What we'd really like is tools that can automate all aspects of learning from data. And I don't mean necessarily by automate, I don't mean necessarily replacing the human, but actually providing tools that make a lot of the kind of small decision-making systematic. And so the human actually can do the more interesting things. Higher and higher up the food chain, essentially, of use of that person's intellect. So almost everything I'm interested in currently revolves around this topic. I'm going to talk very briefly about 3 of these things in essentially a couple of slides each, and then I'll wrap up. So the 3 that I've picked to talk about today are Bayesian optimization, probabilistic programming, and the automatic statistician. Okay. So probabilistic programming is, for me, really the next wave of exciting advances in machine learning. If we can get it to work, this will be really revolutionary. And the idea here is that current probabilistic machine learning is very error-prone and time-consuming because people have to derive algorithms, implement them, and debug them by hand. And just like compilers make it possible for people to write high-level computer programs without knowing anything about machine-level code, we really want the same sort of acceleration for probabilistic modeling. And that's the solution. The solution is you write down your model as a computer program that could generate data. That's what I told you a model was. It was a mechanism for thinking about data that you could generate. You might be just generating some outputs given some inputs, but you're still generating something. And the idea is, rather than writing your model as a set of equations, you write it as a computer program in a general-purpose programming language, okay? A Turing-complete programming language, ideally. Okay. So models are like simulators. But that's not good enough. If we just had that, we could forward simulate from our model. But really what we want to do is we want to learn given some real data. We have our model, which we can forward simulate from. Now we have some real data. And the question is, what settings of the parameters of this model would match the real data? That's the inverse problem applied to computer programs. Okay? That's actually applying, what we really want to do is apply Bayes' rule to a computer program. Condition the executions of the computer program literally on observing the data that we observed. And that's, we can do that. That's the remarkable thing. We can do that with these universal inference engines. And under the hood, actually, these probabilistic programming languages involve, variations on many different existing computer programming languages. I've listed a bunch of them here. The main one coming out of my lab is called Turing, which is based on the scientific computing language called Julia. So you write your programs in Julia, and then you can run them in this setting. But you have your favorite languages if you want other languages to use for this. And then under the hood for the universal inference engine tend to be methods like Markov chain Monte Carlo methods, or variational approximations, or sequential Monte Carlo methods, particle MCMC, etc. But the user doesn't have to know about that. That's the good news. Okay. I'll just skip through this quickly. This is an example of a hidden Markov model written in our language Turing, and if I wanted to write a Bayesian hidden Markov model, I would uncomment this one line of code, and I wouldn't worry about, rederiving the algorithm for that. It makes it very, very easy. Okay. The second thing I wanted to talk about is Bayesian optimization. And Bayesian optimization tries to solve the following problem. The goal is to optimize some black box function that is expensive to evaluate. So f of x is some function we want to optimize, and the problem is that every time we evaluate f of x, that might cost us either money or time or compute or something like that. So we want to optimize it in as few evaluations as possible. The solution to this is we treat this as a problem of sequential decision making, and we model the uncertainty in the function. So the computer thinks about where to evaluate next, because evaluating is expensive. And this has a huge number of applications, everything from robotics, how do I optimize the gait of my robot to move quickly? Or drug design, how do I optimize the design of my molecule to have certain properties? Or even in machine learning applications like neural network hyperparameter learning. So I will skip over this, but this is basically a recipe for how Bayesian optimization works. And it's really applicable in a lot of settings where evaluating function is expensive, evaluating derivatives is hard or impossible. There is noise in the function evaluations. There might be noisy constraints, etc. The last thing I want to talk about before moving on to questions is automating model discovery. And this is the idea of the automatic statistician. The problem this is trying to solve is that data are ubiquitous, and there is a great value in that data, but there aren't enough data scientists to analyze all of this data. So can we make our data scientists more efficient by developing a system that automates certain aspects of model discovery from data? This is kind of an ambitious goal, which is useful in helping us understand how difficult the problem is, right? So here's the ingredients of the automatic statistician. The framework involves you take in some data, and then you search over possible models that can explain patterns in the data. When you're searching over models, you're not searching over a list of models, but you're actually going to be generating new models by exploring a whole language of models. Think of it as a grammar over possible valid models that might have infinitely different models inside of it. Now, that language of models is very hard to search, but you evaluate different models to see how well that model fits in with the data. And this is where we're going to use Bayesian-Occam's razor to determine models that are neither too simple nor too complex for the data set at hand. And then once you've found a good model, you can do the usual things with that model, for example, prediction, but you can also do a couple of things that I think are rather more novel. One of them is take your model and translate it into a report that the user can read. Okay, so this is the opposite of a black box. This is trying to be as transparent as possible, giving a fully interpretable representation of the patterns that have been found in the data. And then you can also do model checking, which is the system being self-critical and trying to determine aspects of the model that might be falsifiable from the data. Okay. So I won't go into all of this. We use Gaussian processes for the automatic statistician. And then the grammar over models involves the grammar over ways of designing Gaussian processes. And we can apply this to time series data. I'll just give you some examples. Sorry, I'm just going to skip ahead and give you some examples. So here's an example analyzing the famous Mauna Loa Keeling curve. This is a carbon dioxide concentration on top of the Mauna Loa volcano. This is a data set that's used by climate scientists to understand global warming. And here is a bunch of this one-dimensional time series. And here is the automatic statistician learning a model from the data. So it's interpolating pretty well, but this is extrapolations. Its extrapolations are quite poor. And then as it searches over its grammar of models, it finds a better and better model of the data with more and more reasonable extrapolations. And in the end, it represents a model in a particularly abstract way, but then it translates it into a report, which is this 5 to 15 page document that a user can read. Here is for another data set, the executive summary in the report. This is text that was generated by the algorithm once you give it the data. Here is the first page of these 5 to 15 page reports that are generated by the algorithm. These are quite readable. We designed them so that a numerate person would be able to read them. And you can look at more examples if you go onto this our website, Automatic Statistician. Okay, this ends up performing well because being systematic. I won't go into this, but this is the standardized root mean squared error, which is the amount of error of a system predicting on new data, averaged over 13 data sets. So box plot of that kind of error. These are our automatic versions of our automatic statistician, 2 different versions, and this is a bunch of competing methods. And the point I want to make here is that the goal of the automatic statistician was interpretability, but actually by being systematic searching over data sets, we also end up getting good accuracy. although there is always a trade-off between the two. And that's it. So I wanted to just wrap up with this thought that probabilistic modeling offers a framework for learning from data. And I've talked about 3 different topics in this theme of automating machine learning. And this is a review paper, if you're interested in this, from a couple of years ago, where I talk about all these things in more detail. And I'll end just by thanking a whole bunch of collaborators I've had over the years. Okay.
Thank you very much. That's an enlightening lecture. And now we have time for some questions. So this will be part of the fun. See, this is a microphone. Ready?
So my question is, when you estimate these uncertainties, you're going to have a bias based on what you're using to approximate this Bayesian problem or Bayesian inference problem. What's your view on that?
Yeah, I think this is an excellent question. So even though ideally as a Bayesian, you would put in a prior and get exactly the uncertainties that you believe in given that prior, there are 2 additional sources of uncertainty, which one of them is, well, what if you didn't actually believe that prior? So what if somebody else believed a different prior? How would your answer be different? And one could analyze that sensitivity to the prior. But the more difficult aspect of uncertainty is because we have to make approximations, then because the exact computations are intractable, we have to do approximate Bayesian inference. We get an additional source of bias, either positive or negative bias in terms of the uncertainty that we compute, right? I don't have a good answer for that. But this is where it's quite useful to marry Bayesian methodology with some classical statistics that can give you bounds on performance or theoretical guarantees. But also, more practically, this is where, even as a Bayesian, it makes sense to leave out some data. The Bayesian framework doesn't say hold out data. But if you're a bit unsure about your prior and your approximation method, hold out some test data and just validate against that test data. I think ultimately that's the best thing to do.
Okay. Thank you.
Thank you. It was a great talk. Reading about recognizing pedestrians and other things on vehicles, one reads, back in the day, the cameras were so bad that the computers were only seeing blobs of people. When are you able to say no? You have vast experience in handling, in seeing these problems. When do you say no, the data is not sufficient?
Again, that's an excellent question. The problem is that you might have a lot of data, but you might have a lot of data from a limited set of environments. Okay? So, for example, you might think you have 1 million data points of camera scenes, but you might not have encountered, fog when the pedestrian is on a wheelchair, or some combination of features in the world that is actually quite rare, right? And so my feeling is that we have to have multiple approaches to safety in systems like that. So you don't want to just be relying on a camera doing pedestrian detection. You also need to have range sensors for distance, radar, LiDAR, etc., and then combine all of these to get safety. But even then, you're not going to get the kinds of guarantees that like a proof system would give you in a formal verification system, right? You just can't get that because you're interacting with the real physical world. On the other hand, humans don't come with terribly good guarantees either. And we have, unfortunately, about 1 million people, die in road accidents around the world, right? I think that's correct. I could be wrong about that. So there's a lot of room for improving that.
Any more questions? Are you ready? Okay. Whoops. Any more
There's a question there.
So also thanks for a really exciting talk. Let me just ask you, how much better do you think that computers or algorithms should be than humans for us really accepting this? You just alluded a little bit into it with the traffic, but I think it also covers all what you said and also about the uncertainty.
Yeah. It's very much application specific, obviously. So in computer games, there's very little risk if your computer is not very reliable, right? But of course, in self-driving cars or medical domains or criminal justice, machine learning systems are being used in the criminal justice system in the US, which is actually quite worrisome to make some parole decisions, in credit decisions, all sorts of settings that where we as a society would really like machines to be very, very good. Now, the sort of there's the rational answer, and then there is the societally acceptable and legally acceptable answers. The rational answer is, we should switch at the point where a machine is more reliable than a human, right? I mean, there's sort of no rational reason why we shouldn't do that. But I think the bar for machines is going to be much higher, both legally and societally. If there is an accident involving a machine making a decision, society is going to be much less accepting than an accident when a human makes a decision, because we're already used to humans getting into accidents. And so I don't know where those cutoffs are, but I know that they're going to be higher. Yeah.
Do we have a last question? No? Last chance? Well, we're going to have a reception here outside, and you can approach Zoubin outside and ask more questions if you like. And then I'd like to thank you again for this wonderful talk.
Thank you.